go. And we're double checking, making sure the audio part is also recording. All right, so we are recording, and we talked about the representation of signed numbers as well as how to compare numbers. Okay, are there any questions related to that last part, especially how we compare numbers? So let me open a new tab so we don't lose track of where we are in class. But I just want to kind of bring us back to the comparison of values, okay? Because it's, in terms of hardware, it is exactly the same. We use the subtractor for comparing. That's it, okay? The question is, how do you look at the result after a subtraction and see whether a value is less than another value? And then you have to take into consideration, are we looking at values that are signed or values that are unsigned? Okay, so that was the thing that we were working on Tuesday. Are there any questions about any of those particular topics? The most important part to remember is we use exactly the same subtractor to do both. Okay, so we use the same subtractor to compare values that are signed and values that are unsigned. Okay, we do represent values that are signed that are slightly differently because we have negative values to represent as opposed to unsigned values where we don't have to worry about negative values. But because of that, we have to look at the result differently. Okay, just to summarize, okay, I'm debating whether to use my document camera or just to use the whiteboard. Which way works okay for you? Camera? Okay, fine. We'll set up the camera. Okay. So since we're looking at exactly the same subtractor, so it is not the mechanism of the subtractor that is really telling us the ordering of values. It is by looking at the signs, the most significant bits, and also the borrowed bits that will tell us, how the numbers are ordered. When we talk about ordering, we are not talking about general ordering either. All we can tell is whether the subtrahend is greater than the minuend or not. Okay, or if you look at it the other way around, which is better, is we can only tell whether the minuend is less than the subtrahend or not. So that's the only thing we can tell after a subtraction by looking at the flags. So we'll set this up again. It would be kind of cool if this thing can self-assemble like a transformer. And those days are coming, I hope. In about 5 years, I can have this rig, and I just need to call its name or press a button, and it will come out and kind of self-assemble along with my external hard drive and my mic. It will set up everything for me. And I just keep, and it will replay recordings of my lecture of the prior semester automatically. That's the ultimate, way of teaching classes. Okay, so we got that. We just need paper and set up the webcam. Okay, just a reminder, no food, drink, phone, or kids, during class time. Plain water is okay, but anything other than that, please wait until after the class. You can probably, I'll let you guys have, plain water with caffeine, dissolved in it. How about that? But not coffee, okay, just caffeine. You can have the compound dissolved in it. All right, so we're almost there. And, just to make the class effective, I have to allow the use of cough drops because I have one in my, yeah. Because without that, I really doubt that I can get through the class Okay, so we got, oh, I just bumped it.
Yep.
It would be nice if it has it can project a laser beam, so it can kind of give me just the frame that it's projecting or what it's recording. So that will make it a lot easier to align. All right, so it's good enough. And I need a pen. The only reason I kind of hesitate to use the document camera is it records my hand too, so that can be distracting. And, oh, there's one right here. Cool. There we go. All right, so what we are doing is we need to focus on the subtraction. And when we talk about the subtraction, okay, so this is where you're kind of familiar with. I'm not even going to bother with the intermediate borrows in the subtraction. So we have three pieces here. We got, this is called the minuend. This is called the subtrahend. And we just refer to this usually as x, this is as y, and this is the difference. And we just call this d, okay? The mechanism to get the difference out of the minuend and the subtrahend is identical, okay? Regardless of whether you're dealing with signed values or unsigned values, okay? So that part is the same. They use exactly the same gate. It is designed exactly the same way. So what is different is how do we look at the result after this whole thing? But when I say look at the result, I'm not talking about all the bits here, okay? So there's some additional stuff here that we need to look at. There's one extra borrow here, okay? This is one extra borrow that we know as borrow out, right? Okay? Which is the overall borrow. After you do the 4-bit subtraction, 8-bit subtraction, 32-bit subtraction, and whatnot, do you still end up with a borrow of 1? Okay? You either yes, I still end up with a borrow of 1, or no, I do not end up with a borrow of 1. The borrow flag is useful, but only when the values that you're dealing with are unsigned. Okay? So if you're only dealing with unsigned values, the borrow flag by itself is going to indicate whether the minuend is less than the subtrahend or not. Okay, so I'm just going to write it down here. Okay, so b equals to 1 if and only if. Okay, this is the symbol to represent if and only if, which is really kind of important. I cannot say if, I cannot say only if, I have to say if and only if. Okay, if and only if x is less than y, and this is seeing x and y as unsigned values, or I can look at x and y as bit patterns representing only unsigned values. So for 4-bit numbers, x and y can both represent values from 0 all the way up to 15. Okay, are we okay with this? Now, the if and only if is important because it means that if x in fact is less than y, b has to be a 1. If x is not less than y, then b has to be a 0. But it also flips around and say, if you look at b, if it is a 1, it means x is less than y. If b is 0, then x is not less than y. Now, if x is not less than y, by looking at just b itself, we have no idea whether they are the same or not. Okay? We have another flag to deal with here, equality. That's an easy one. Okay? So when you look at d, okay, so let me go ahead and expand d a little bit here. Okay, so I look at d as dn minus 1, dn minus 2, all the way down to d0. In other words, this is just a notation for the individual bits of the difference. Okay, d subscript n minus 1 is the most significant bit because we count from 0. D subscript 0 is bit 0 of the difference, which is the least significant bit of the difference. Is that okay? Okay. So the z flag, okay, the 0 flag, if I want to avoid the use of the big conjunction symbol, I can just go ahead and expand it. So I can say d subscript n minus 1 or d subscript n minus 2, or all the way down to d0. Okay, remember the plus means disjunction, it means or. Okay, if you take a negation of this entire disjunction, that is your z flag. In other words, the z flag is a 1 if and only if the difference is in fact 0. Because that's the only time when the disjunction itself will give you a 0. But since we're looking at the negation of the disjunction, the 0 will turn into a 1. Is that part okay? Yes? Okay? Alright. Alright, so now we have to throw in some other, kind of nasty stuff. The nasty stuff has to do with what if x and y are representing signed values as opposed to unsigned values? Okay? Because that's when things really go bad. Okay. So now we have to look at the sign of these particular things. In other words, we look at the most significant bits of x, y, and d. They are now significant. Is that part okay? So in this notation, I can say, x subscript n minus 1 is the sign of x, y subscript n minus 1 is the sign bit of y, and then d subscript n minus 1 is the sign bit of d, because the sign bit is none other than the most significant bit of a binary bit pattern. But it only applies when you know that the binary number is representing a signed value. Is that okay? So we don't even ask what is the sign bit if you say, oh, I know these binary numbers are only representing unsigned values. So we only care when they are representing signed values, things that can go negative. Is that okay? Okay, all right. So the sign flag, okay, which has its own name, which is just s, is nothing more than just d subscript n minus 1. In other words, the sign flag is just the most significant bit of the result of the subtraction itself. Okay, and that is the most intuitive, indicator of whether the minuend is less than the subtrahend or not. Because when you look at a normal subtraction, if the minuend is less than the subtrahend and you're dealing with signed or even unsigned values, the result is going to be negative.
Yeah.
Right? It makes perfect sense, right? If you have just a normal subtraction, x minus y, okay? If x is less than y, doesn't matter whether they are signed or not, then whatever you add up here is going to be a negative value if x is less than y. Okay? So that seems to make sense that we can just rely on the sign flag alone to tell us whether the minuend is less than the subtrahend or not. But the problem is, in the subtraction, we can end up with a value that is out of range. Okay, so we can end up with a situation like this. I cannot remember whether we used this example last time or not, but we can use different examples. It doesn't really matter. It's the same thing. So when you look at 13, which is clearly less than 6, right?
Yeah.
Because in a normal subtraction, we say minus 13 or negative 13 minus 6 is negative 19. So this negative quality of the difference tells us that negative 13 is less than 6. Makes perfect sense, okay? But when you look at the binary subtraction as a 4-bit subtraction, we have a problem. Because 13 is I cannot do negative 13 because that's out of the range of a 4-bit number to begin with. So let's pick something else.